A Portland Community College Mathematics Telecourse. A course in arithmetic review produced at Portland Community College. This lesson is going to lead us into a topic called scientific notation, an extremely valuable lesson if you're going to go on into any technology, science, engineering, or use of any scientific calculator. But before we go too far, let's review what we mean by a power 10. It's simply any number which can be written as a product of tens. See, we had agreed that if you're multiplying two tens together, we simply write 10 with a small 2 to the right and up high, which we call an exponent. So if I had 10 times itself twice, or 3 tens being multiplied, we would write that as 10 with an exponent of 3. If we had 4 tens being multiplied, we would write that as 10 with an exponent of 4, and we would verbalize that as 10 to the 4th power. And by special definition, 10 by itself, we will agree is 10 to the 1st power. And the number 1, by special definition, is simply 10 to the 0 power. Now notice that the powers go up. On 10 to the 0, there is 1 with no zeros behind it. 10 to the 1st is a 1 followed by 1 0. 10 squared is a 1, if you would, followed by 2 zeros, and so on. Recall this from chapter 1. We'll be using that a lot in this discussion. Now, for what we're about to develop, it's going to be very convenient to make a slight alteration to this power 10 notation. Of course, we're familiar already that we can write these powers of tens in decimal form. In fact, that was the reason for the invention of the decimal system. But now let's make this one agreement. Rather than writing these powers of tens in denominators, let's write it that way and use a minus sign in front of the exponent. And the minus sign will mean by agreement the reciprocal of 10 to the 1st, the reciprocal of 10 to the 2nd, the reciprocal of 10 to the 3rd, and so on. This is simply an agreement to notation. Don't look for the logic or the rationale. It's simply an agreement we're making that's going to make a very nice system in a few moments. So in short, the negative exponent will mean by definition simply the phrase 1 over or the reciprocal of. We call that as we go on in this lesson. Now let's write this in standard notation. Recall that we had simply said write a 1 with 6 zeros behind it. Or if you would, 1 million means 1 over 1 followed by 6 zeros, or 1 millionth. Now if I were to divide this out, you would get 0.1234, and not 6 zeros, but 5 zeros and a 1. These are all the same thing. So we could verbalize this way. If it's a positive power, write down a 1 and follow it by 6 zeros. If it's a negative exponent, start with a decimal point and mark off 6 places to the right. 1, 2, 3, 4, 5, 6, with the 6th place ending in 1. Now at first it seems as though there's a slight difference. Here we stick on 6 zeros, here 5 zeros. But let's look at this from another angle where we'll see really they're very compatible and saying about the same kind of a thing. In both cases, let's start with a 1. And of course, with all whole numbers, the decimal point is just to the right. Now let's think this way. If the power of 10 is positive, make this one larger by 6 places. And then, of course, as we create extra places, we use placeholder zeros. Now, let's again start with 1, but let's make it smaller. Let's interpret the negative that way, to make smaller by 6 places. So make smaller by 1 place, 2, 3, 4, 5, 6. So if we view the positive exponent as make larger by that many places, and the negative exponent as starting from 1 making smaller by that many places, we're saying the same thing. Make larger by 6 places, make smaller by 6 places. Okay, recall it. That's going to make several problems coming up soon very easy. Now, any 1 followed by nothing but zeros, or 1 preceded by nothing but zeros in decimal point, we refer to as powers of 10. If it's larger than 1, it'll have a positive power. If it's a decimal less than 1, it will have a negative exponent. Now this one, if we were to get up to 1, I'd have to count for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places. So we'd call that 10 to the 11th power. Now note, it's not zeros I'm counting, it's places. So here to get back to 1, and you get back to 1 not here, but there, just as I did here on that one. So I'd have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So this we will express as 10 to the negative 9th power. So it's getting to that 1 that is a critical thought. I have to move it 9 places to get to 1, and since the number is less than 1, it's a negative exponent. Here I have to move it 11 places to get to the 1, so we call that 10 to the 11th. Now, having a number multiplied or divided by a power of 10 occurs very, very frequently in science. It's almost the rule in science. But there's a shortcut for doing this, which makes it rather convenient. Write down the digit of the number you're multiplying by that power 10, and the decimal point is there. Now, if you're multiplying by a positive power of 10, think that I wish to make this number bigger by that many places, 6 in this case. So to make it bigger, if I go this way, the number gets bigger. If I went this way, the number is getting smaller. So I wish to make the number bigger by 1, 2. Now to keep moving, I need some extra zeros. 3, 4, 5, 6. Let's check. Bigger by 1, 2, 3, 4, 5, 6. And indeed, if I were to write this as 1 followed by 6 zeros, then multiply by the conventional way times this, I would get this. So again, if you're multiplying by a positive power 6, you simply make the number bigger by that many places, inserting zeros if you need to. Another more formal way of saying this is to multiply a decimal by a power of 10, move the decimal point to the right as many places as the exponent value, and insert placeholder zeros if extra places are created by that process. That's saying from a slightly different angle what we just told you by that example. That is, to multiply by a positive power of 10, make the decimal number larger by as many places as the value of the exponent. What happens when we're multiplying by a negative power of 10? What we call a negative power of 10 is 1 over 10 to that power times this number. And of course I can write that now as 4.32 divided by 10 cubed. So, first note, multiplying by a negative power of 10 is the same as dividing by its positive equivalent. Now the shortcut we're going to give you for this procedure is simply this. If you're multiplying by a negative power of 10 or dividing by a positive power of 10, your number will get smaller by that many places, 3 places if you don't look at the negative sign. So, our rule, when multiplying by a negative power of 10 or dividing by a positive power of 10, make the number smaller by that many places. So I've made this number smaller by 3 decimal places. That rule once again, to multiply a decimal by a negative power of 10 or to divide by a positive power of 10, move the decimal point to the left as many places as the exponent. And again, insert placeholder zeros if they're needed because of newly created positions. Or, saying the same thing slightly differently, but still saying the same thing, to multiply by a negative power of 10, which is the same thing as divided by a positive power of 10, make the decimal number smaller by as many places as the exponent value. An example. I wish to multiply this number by a negative power of 10. The rule we just gave said make it smaller by 5 places. Smaller by 1, 2, 3, 4, 5 places. And I need to insert the placeholder zeros. Here's a number written in the form that we will refer to from here on out as scientific notation. Anytime you have any number, we'll call that number just n now to stand for any number, where the number itself is greater than or equal to 1 or less than 10 and less than 10, followed by the product of a power of 10, positive or negative, we will call that kind of a number scientific notation. Scientific notation is a very convenient way of expressing extremely large or extremely small numbers. It's so important that all scientific calculators are programmed, pre-programmed, to work automatically with scientific notation when one of its numbers gets too large or too small. Here are 2 numbers written in scientific notation. A decimal number between 1 and 10, followed by a product of a power of 10. Again, a decimal number between 1 and 10, followed by a product of a power of 10, in this case negative. Let's write this in place value notation or scientific notation. Place value notation is a terminology your text uses. Remember, we just stated that to multiply by a positive power of 10, you simply make this number bigger by 5 decimal places. So we started here, 1, 2, 3, 4, 5. So this scientific notation is simply another way of saying 673,000. Now if you're multiplying by negative power of 10, our shortcut stated to make it smaller by 4 places. So smaller by 1, 2, 3, 4, the decimal point goes here. Now let's see, 10th, 100th, 1000th, 10,000th, 100,000th, millionth. So this is another way of saying 205 millionths. Now at this point, there's not much advantage of this number over this number or vice versa. This form we call scientific notation. This form we call either the place value name, and many scientists will call it the standard notation. Actually, in science, this is more of a standard. This will be used for very large or very small numbers, far more than this form will. Let's try reversing the process, writing this number into scientific notation. That means we want the decimal point behind the first non-zero digit, followed by a power of 10. So our only question is, what power of 10 can we place here to justify putting the decimal there rather than way back here where it legitimately belongs? Well, if it were here, then to get it back to where it should belong, I'd have to make it larger. That tells me a positive exponent of 1, 2, 3, 4, 5, 6, 7, 8. So if you want to put a number into scientific notation, put the decimal point behind the first non-zero digit, then ask yourself, if it were there, how would I have to move it to get it back to where it really belonged? Well, I'd have to make it bigger. That's multiplying by a power of 10 with a positive exponent, 8 places, exponent 8. Let's use that same idea to write this one in scientific notation. First, scientific notation says I want the decimal point there. So I'll have to adjust with a product of a power of 10. Now, if it were there rather than here where it really belongs, to get it back to where it really belongs, I'd have to make it smaller by 1, 2, 3, 4, 5, 6 places. So negative exponent says I'm making smaller by 6 places. So this we call the place value name, this the scientific notation. In later lessons and this extended lesson, you will see this being used on the calculator and to express extremely large and extremely small numbers, which would be almost impossible here. Just one short example. This is a number used in measuring the cross-sectional area of atoms. Looks very simple here, but let's look at this number in place value notation. See, almost impossible to write on the paper, as we said. So the scientific notation is a much better way of saying this very, very tiny number. And the same thing with extremely large numbers, which occurs in physics and astronomy, and atomic physics in particular, very frequently. Let's clarify a point, a common error made before perhaps you even make it. Let's say that for some reason you wish to write this number in scientific notation. Now, by the definition we've just given, it means we want the decimal point behind the first non-zero digit. So I want the decimal point here rather than back here where it properly is. So we put it behind that first non-zero digit. Then we adjust it by multiplying by a power of 10. So to get this back to where it originally was, we can see I'd have to make this 4.8 bigger by 1, 2, 3, 4, 5, 6, 7 places. And bigger means to make a positive exponent. That's fairly simple, isn't it? But there's a tendency for many students who aren't listening very close to that phrase which said to be in scientific notation, we want the decimal point behind the first non-zero digits. And there is a tendency then to put the decimal point simply at the end of whatever the digits are, the non-zero digits, and then to adjust by a power of 10. And their reasoning would be, gee, if it were here, I'd have to make it larger by 1, 2, 3, 4, 5. So they say this. Now it's important to notice that this is a correct equivalent to this. This is really equal to this, and this is equal to this. But the point you need to realize is even though this is a correct way of saying it, we will not allow ourselves to call it scientific notation. To be called scientific notation, we insist that the decimal point be behind the first non-zero digit. This we'll just call in general terms a power of 10. And there are many correct ways of writing this by using powers of 10, but only one that we will allow ourselves to call scientific notation. Be very, very clear on that. Scientific notation means the decimal point is behind the first non-zero digit, reading from left to right. Now, as promised on the last lesson, let me show you something about the scientific calculator and very large or very tiny numbers. If you were to ask to multiply 32 million times 43 million on a standard 4-function calculator, you'll find that you could get this onto the calculator. After all, we had 32, then 1, 2, 3, 1, 2, 3, 6 zeros. It fits. And then if we say times the next number, 4, 3, 1, 2, 3, 4, 5, 6, that fits too. So the numbers fit on our calculator, but if you were to say equal, on most standard calculators, the answer is so large it won't fit on the calculator. So a standard inexpensive 4-function calculator would simply say error or give you some kind of message which says, hey, I can't do this, it's too large. The answer is. Watch what happens to a scientific calculator. As soon as I hit the equal, it does something rather strange. It has 1.376, and there's no doubt that this product is certainly going to be larger than 1.3. It's going to be up in the billions and billions. So what happened? But notice there's a little blank space there. And on the scientific calculator, what that blank space says, without actually writing it out for you, is that this is times 10. So interpret that little space as times 10 to that exponents. So what a scientific calculator will do, so it doesn't lose your problem because the screen can't hold it, it'll work the problem anyway, and if it's too large for the screen, it will automatically click over to scientific notation and give you the answer in scientific notation, because in standard notation, this is much, 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 much too long. Isn't that convenient? Now watch how if I'm multiplying by two very tiny numbers, the same thing happens. Here, this number again would fit on the screen, and so would this, but their product would not. It'd be too many decimal places. But let's see what the calculator does. 0.1, 2, 3, 4, 5, 6, 7. See, it fits. Times 0.1, 2, 3, 4, 5, 6, 8, and that fits. But the product will not fit. So let's hit an equal and see what it does. Again, it gives me the number 5.6, and notice 7/8 is 56. But now there is that little blank space with a negative. Okay, when there's a blank space or a small number ending your screen output of your calculator, that means the calculator is trying to tell you it's times 10 to some exponent. And the small number, or the number following this space, is its exponent. So now this says if you were to take 5.6 and make it smaller by moving the decimal point 13 places, that's what this number is in standard notation. So note, if we were forced to use standard notation for everything, even calculators could not do a lot of problems. But if the calculator can work in scientific notation, at least it can keep the front important part of the decimal and convert the rest of it to a power 10 and report our results in scientific notation. Now let's look at the reverse of that. Here is a number in scientific notation, and if I were to write this in standard notation, it's much too long to even enter into the calculator. So does that mean the calculator can't even work with it? No. Again, a scientific calculator will allow you to enter a number in scientific notation form. So we would enter this decimal portion here, 4.13. Now we need some way to tell a calculator that I'm going to give you a scientific notation number. So on most calculators, it's the EXP key, this one right here. On many calculators, it might be another key, so you have to find that from your directions. But on this one is EXP, so I push that. Now note, it's got a little blank space. That means it needs the power 10. So now I simply put in 12. So 4.3 space, which means times 10 to the 12th power. Isn't that nice? Now how about a negative exponent? How would we do that? Let's say this very tiny number, 3.57 times 10 to the minus 8. First we enter the decimal portion, which is 3.57. Then to tell the calculator we're entering a scientific notation number, we push the EXP key. Is ready for the exponent. So we put in the exponent of 8, but I want it to be negative. So up here, right here, is a key which you might not be able to see, but it looks like this. Plus, slash, minus, which means change signs. So I push that change sign key, and now that has become minus 8. So 3.57, space means times 10 to the minus 8 power. So in fact, a scientific calculator can work in scientific notation. And in science technology, that is almost always the case, rather than standard notation. Of course, there's much, much more to this scientific notation than we possibly have time to explain in this very short lesson. So in your future science classes and other math classes, do expect to see this being used very, very heavily. And there will be more teaching about this. This lesson is asking you to get into and out of scientific notation and multiplying and dividing by powers of 10. If you have that as you go into the next lessons, the rest of this will become very, very easy. This is your host,